In this section we continue our study of applications of the definite integral, but before we start, let's review what the two applications that we've studied so far. One, we learned that if we wanted to find the area between two curves, let's say this is between A and B, the area between F and G, this area here, that we could look at a representative rectangle. In other words, we partitioned the interval AB and we looked on the ith subinterval and estimated the area just over that ith subinterval with the area of a rectangle. And we said that the area of this rectangle, because it's vertical, would be, well, its length times its width, so it would be f of x minus g of x dx. And we would integrate dA to get the area. We'd integrate that function f of x minus g of x. But all I want you to see here is that we partitioned the interval, we looked on an arbitrary little subinterval, and we saw that we could very closely approximate the area just over that subinterval with a rectangle. And so we found the area of that rectangle and integrated over that to find the total area. The other thing that we did was we looked at a curve and we said, well, what is the length of that curve? And we then said, well, all right, maybe that we introduce an axis and we say it's from A to B, and let's say this is a function f. And we again partitioned the interval and we looked on a little subinterval, an arbitrary subinterval, and then we said, well, you know, if that is a really narrow subinterval, the length of the arc over that subinterval is just the length of the line segment. And so we used the length of the line segment to develop a formula for L, and it was the integral from A to B of the square root of f prime of x squared plus 1 dx. So we've had two applications. Now we get to the third, and that is volume. Just like we did for area and arc length, we will develop a Riemann sum that estimates the volume of a solid, but only a certain kind of solid, a solid that has parallel cross sections that have the same formula for area. So here's a picture of one. No matter where you slice that, notice we're looking, I have yellow here. We're looking at a solid that lies over an interval from A to B, and this solid, no matter where we slice it, perpendicular to the x-axis at some value of x here. Here's x. At some value of x between A and B, if we slice perpendicular to that axis through the solid, we get a cross-section. And that cross-section has a common area formula. And if that's the case, then we'll see how we can develop a Riemann sum and find a formula for the volume of such a solid. Now we know that for area we use little rectangles to estimate small pieces of area, and for volume we are going to use a common volume that you've all used before, but maybe not in this generalized sense. And let me draw one for you. It's called a right cylinder. A right cylinder. And what that means, it's not a very good picture there, but it means that the top is congruent to the bottom. The top face is exactly congruent to the bottom face, and the top is parallel to the bottom, and the top lies directly over the bottom. In other words, the the side is perpendicular to the faces, let's say, the top and the bottom. So an example would be a rectangular box. That's a right cylinder. Or a right circular cylinder, like a can. These are examples. But in general, it's just, here it's length times width times height. Length times width times height is the volume. And here it's pi r squared times height is the area, volume of a cylinder. This is the volume of a box, the volume of a cylinder. In general, if you just have the top exactly the same as the bottom, and one is right over the other, in other words, the sides are perpendicular, the volume in general is this. The volume of a right cylinder, V, is equal to the area of a face, in other words, the top or the bottom, times the height. So look, cylinder, pi r squared times h, the area of the top times the height. Length times width times height. Length times width is the area of the top times the height. And in general, that is how we find the area of a right cylinder. Okay, so here's a picture of that solid, and it has, if you slice it in any parallel or perpendicular to the x-axis between A and B, it has a formula for area. So let's partition AB, partition the interval AB from here to here, and let's look on a little ith subinterval, a general subinterval, and look at the little slab of volume there, the little slice of volume. If that subinterval is very, very, very narrow, we could say that this slice, let me write it here, this ith slice has volume approximately equal to the volume of a right cylinder. So what you can do is just choose a c sub I, any one you want. Let's say that's it right there. Choose c sub I anywhere in the ith subinterval, in other words, a sample point, and take the slice right there, and we know that it has a formula for its area. And so the area of that blue thing that you see there would be A of c sub I, the area of the slice taken at c sub I. And then we would multiply that by delta x, and we have the volume of a right cylinder with faces that are the blue piece. So it's not exact, but it's approximately. And we could say V sub I, then the actual volume over the ith subinterval is approximately equal to of the area of the slice taken at c sub I times delta x, the volume of a cylinder. And the volume then of the whole thing is approximately equal to the sum from I equals 1 to n over the partition of A evaluated at a sample point taken from each interval times delta x. And do you recognize that? What kind of a sum is it? It's a Riemann sum. So we can say then that the volume, if you have a solid where you can take slices perpendicular to an axis and come up with an area formula for the cross-sectional area, then we can say that the volume is the integral from A to B of A of x dx, where A of x is the area of the cross-section taken at x between A and B. We'll just read through these steps together. You could put them into your notes and notice that we will follow them as we do a couple of examples. But this is, since we can't draw three-dimensional solids very well, and a lot of these solids are very hard to even imagine what they look like, there's a way to go about it where you don't have to know what the solid looks like. So here are the steps to finding the volume of a solid with parallel cross-sections having a known area formula. The first thing we do is we draw the base of the solid and we sketch in the bottom edge of an arbitrary cross-section. We determine the length of that bottom edge by looking at the equation of the base. And then we draw a cross-section and determine its area formula, A of x or A of y, depending on whether or not the cross-sections are perpendicular to the x-axis, or in the case of A of y, perpendicular to the y-axis. Once we have the area of a cross-section, we get the volume by a definite integral. So really we're not concerned with what the entire solid looks like. We're concerned rather with what is the area of a cross-section. So before we work on the first example, I just wanted to show you from Mathematica what one of these things looks like. In the first example we're going to have a circular base, and the cross-sections are squares. So take a look at this thing. This has the circular base, you can see there, the circular base, and it has this weird shape. You would not be expected to know how that whole solid looks. All you need to know is that it has square cross-sections. If we had a square base with square cross-sections, it would look like a box. We could visualize it. What if it was a square base with semicircular cross-sections? Well, we have this then. Looks like a tunnel. If we had a square base with equilateral triangle cross-sections, then our solid would look like this. But again, you don't really have to envision the entire solid, just what the cross-sections look at. So now we'll do a couple examples using those steps that I outlined. Okay, so we have the base of our solid is a circle. x² plus y² equals 4. So the first thing I do, step number 1, is to draw a picture of the base, and since I have an equation of it, I'm definitely going to put it on the, there's our base, a circle of radius 2, x² plus y² equals 4. Draw the base and write its equation out. And now the cross-sections of the object perpendicular to the x-axis are squares. Okay, that's like the one we just looked at in the Mathematica. Okay, so I'm just going to pick an x, any x. I'm not going to make my cross-section right at 1 because I might think that x equals 1. This is just at any value of x between minus 2 and 2. And imagine a square standing on top of that. That's the bottom edge of a cross-section. So I said in step number 2, actually draw the cross-section. So this bottom edge right here is the same as I drew there. In fact, here, let me make that red, and here is the red. And that square is just standing on top there. Now we want to know the area of the square, A of x, because it's being taken perpendicular to the x-axis. So what is the area? Well, it's the area, we know, A of x, is going to be the side length squared. We have to figure out what that is, this length right here. Well, we're going to find that by knowing what this point is. That point we could call xy. And so y is from the x-axis up 2. So it would be 2y. So it's 2y squared, or 4y squared. But of course, this is a function of x. We want it in terms of x, but we can see that we can easily find the equation in terms of x because y squared is equal to 4 minus x squared. So I go back here and I can write 4 times 4 minus x squared. And so my volume then, I'm done. All I had to do was find the area of a cross-section so that the volume is equal to the integral from -2 to 2 of 4. I guess I'll factor that out there and just write 4 minus x² dx. And let's see, I don't have this figured out, so I'm not going to do the whole thing, but this would be 4 times the quantity, 4x minus 1/3 x², evaluated between the limits. Well, I'm running out of room there. Let's see. Evaluated between the limits, -2 and 2. So you can plug that in and find the actual volume of that object, even though you couldn't completely picture it in your mind. Here's a second example. Let's draw the base. We won't be able to picture this very well, but we'll draw the base. Step number 1. In the first quadrant, it is the region bounded by x² and y equals 4. Okay, so y equals 4 and y equals x². So this is the base, this region here. And I want to draw a cross-section, and in this case I'll draw it perpendicular to the y-axis. I could draw it perpendicular to the x-axis, but it's just simpler this way. The equation will just be the x-coordinate of the point. So let's label that point x, y. And there's the bottom of a cross-section, and the cross-sections are semicircles. Cross-sections are taken perpendicular to the y-axis. It would be a different solid if we took them perpendicular to the x-axis. So the problem will tell you how to take your cross-sections. And let's see now, here is that white line I drew. That's the bottom edge, and the cross-section is a semicircle. So I'll finish like this, and so you can compare. This is the white, this is the white here. And we know that it is simply the x-coordinate of the point. So that distance is x. We want the area of the cross-section. The area of the cross-section would be 1/2 pi r². And r, you see, would be 1/2 x. r would be x over 2, 1/2 x. So the area, I'll put a, or in fact a of y. It has to be a function of y because the cross-sections are being taken perpendicular to the y-axis, and we're choosing the cross-section at a particular y between 0 and 4. A of y then will be 1/2 pi times x over 2 squared. We'll have to put it in terms of y, but right now x is the easy thing to see. So let's see, that's pi over 8, if we get our constants out there, times x². Oh, x² is y. x² equals y. So this is just pi over 8 times y. A of y, the area of a cross-section. So now I have my volume. The volume will be the integral from y equals 0 to 4 of a of y, which is pi over 8. I'll pull the constant to the left, y dy. And that is, well, you can evaluate that. Integrate and evaluate. I got 2 pi, but I did it quickly, so you see if you get the same thing. Okay, so here is what's called solids of revolution. These are solids where you will know the area of a cross-section. So the theory is the same, but they're not ones where we're given the base and described a cross-section. They're called solids of revolution. And I just want to show you some examples that are nicely drawn. If we take take this line right here. This is the line y equals r over hx. And we revolve it around, we take the region from 0 to h, this region here, and we spin it around the x-axis. And every point in space that this region, this yellow region, every point in space that it hits becomes part of a solid of revolution. You see, we have this solid here. And every solid of revolution has a cross-section that is either a circle, like in this case, here's the cross-section. A cross-section taken at x is a circular cross-section. Or sometimes the cross-sections are washer faces or annulus, and you'll see that in the next example. So in this example, we can generate a circular cone by revolving that region about the x-axis. But I'm not going to do the problem right now. I just want you to see some pictures. Here's another solid of revolution. Look on the left here and you see the region bounded by the line y equals 5, x equals 0, the y-axis, and the curve y equals x to the 2/3 plus 1. So you see this region here, and we're going to take that region and spin it around in space, spin it around the y-axis, revolve around the y-axis. And what we get doing that, you can see this region would spin out this, I don't know what we'd call that solid. And of course, you can think of just a little rectangle here, or just a line taken from some y between 1 and 5. That line would spin out the cross-section. So the cross-section is circular. Again, so we will be able to just integrate the area of that circle from y equals 1 to up to y equals 5. So we'll do that example next. Let's see. Okay, so here's how you work a problem like this without having the nice pictures of the solid. Draw the region that you're given and indicate which axis you are rotating around. This last problem that I had up there told us it was the region bounded by the y-axis, this curve, and the line y equals 5. So first I draw that. Then I like to see what it looks like. I draw the mirror image on the other side of the axis, and I draw myself a cross-section. That's what my cross-section will look like. The whole solid, I mean, you could kind of draw a big up there to kind of give it a three-dimensional effect. But what we want is that cross-section, and that will be taken anywhere from y equals 1 to y equals 5. So our cross-sections are perpendicular to the y-axis, and I know that it is a circular cross-section. So the area, I'll put a of y, because we'll be integrating with respect to y, will be pi r squared. Well, but what is r? Let's see. The radius, always use the curve that you know the equation of. I would not be drawing my radius over here. I don't know the equation of that curve here. So I go from the y-axis out, and I label that point x comma y. I know my radius is y. So this is going to be pi. No, my radius is x, excuse me. The radius is the x-coordinate of that point. So I have pi times x squared, the radius is x, r equals x, and I need to put that in terms of y. So we're going to need to solve for x squared. Well, we have y equals x to the 2/3 plus 1. So x to the 2/3 is equal to y minus 1. And now to get x squared from this, I would want to cube it, wouldn't I? So solving for x squared, that's what I want. That's over there in the formula. I have y minus 1, the quantity, cubed. So I'm going to put that in up here for x squared. So I have pi times the quantity y minus 1 cubed. Therefore, my volume is the integral of a of y, so it's going to be pi, I'll factor that out, y minus 1 cubed dy from 1, y equals 1, to y equals 5. And this will be, well, if u was y minus 1, du is dy, so this is simply pi over 4 times y minus 1 to the 4th, evaluated between y equals 5 and y equals 1. I didn't put it in terms of u. And, well, we can plug in 5 there pretty easily and get 1 to the 4th minus 0 to the 4th. So this is just pi over 4. The volume was pi over 4. Okay, here we'll just look at the problem, and then on the next, then I'll do it for you, doing our own drawing, because that's what you'll need to do. The region bounded by the curves y equals x squared and y equals 2x. So, if I was doing this myself, y equals x squared and y equals 2x. That region there, I'd need the intersection point, label the curves. I want to rotate it around the x-axis, indicate your axis of rotation, and draw the solid as best you can. I'll do that in a sec, but here you can see it nicely done. We took this region here in the first quadrant and spun it around the x-axis, and it spins out a solid. Now in this one, when you take the cross section, it's not the full circle. It's the circle with a circle cut out of it. In other words, it's the region between two concentric circles. That's called an annulus, or you could say a washer face. So the area of a washer face will be, well, it's pi times the big radius squared, the big circle, and then cut out the little circle, pi times the little radius squared, or pi times big R squared minus little r squared. That's the area of a washer face. And you all know that. You don't need to memorize that. It's just the big circle and cut out the small circle. Okay, so you start by drawing the region that is going to be rotated around one of the axes. And so I did that, y equals 2x, y equals x squared. Be sure and label any points of intersection. And then we'll actually draw a mirror image across the axis of rotation. This is just to get an idea of what it looks like. You might even want to draw that. Well, I can't. So much harder on this thing. So it looks like that. And now let me take a different color and draw a cross section. Well, it'll have that hole in it. The cross section will be an annulus. So I see the cross section, and then I say, okay, well, that's going to be a of x. We're taking the cross sections perpendicular to the x-axis, and it's going to be pi times the big radius squared minus the little radius squared. Now we have to figure out what those are in terms of x. So let's do that down here. The big radius is from 0 to y on y equals 2x. So the big radius is 2x, and the little radius is from 0 to y on the parabola, and y is x squared. So we have pi times big R, which is 2x squared, 4x squared, minus the little radius squared. X squared squared is x to the 4th. Therefore, our volume is pi times the integral from x goes from 0 to 2. 0 to 2. We could have taken a cross section anywhere from 0 to 2, and we'll integrate 4x squared minus x to the 4th dx. So I'll tell you what I got, but again, I did it quickly and I didn't check it. So I got 112 over 15 pi. You check and see if you get the same thing. Integrate and evaluate. So that is the volume of the solid. Now let's take that same region. I hope you can see it here. This is y equals 2x, and the parabola y equals x squared, and we're going to rotate it around the y-axis now. So we'll need to know the big radius, x on the parabola, and the little radius, x on the line. So we're going to need to solve for those in terms of y, because we'll integrate from y equals 0 to y equals 4. And you see the cross-section there is an annulus. So let's do it on the next slide where we can't see the nice-looking picture. So we have the exact same region drawn, just the way we did when we rotated around the x-axis, but now we're rotating about the y-axis, so I'm going to draw the other side of it, just sketching so I can be sure to see what my cross-section looks like. So in a different color, and by the way, it's even good when you're working on paper to have a pen to do the cross-sections with. There's my cross-section. I could have taken that cross-section anywhere from y equals 0 to y equals 4, and clearly it is an annulus. So a of y, we're integrating with respect to y, will be pi times the big radius squared minus the little radius squared. But now what are those? Well, let's see, take a different color. The big radius is from the y-axis out to x on the parabola. So the big radius is x on the parabola, y equals x squared. So let's see, x is equal to the square root of y, isn't it? Y is positive, so it's the positive square root of y. And we could say the big radius then is the square root of y. And the little radius is, go up here, it's from the y-axis out to x on the line. So x on the line is y over 2. 2x equals y, x equals y over 2. So we can go into our formula and find it. A of y is pi times the big radius squared would be y, minus the little radius squared would be 1/4 y squared. We integrate that to get the volume. So we'll have pi times the integral from 0 to 4 of y minus 1/4 y squared dy. Integrate and evaluate and see if you get what I did. Again, if you don't, you might be right. I did it once and I didn't check it. I got 8 pi over 3. So for your practice problems, you should do, I'll tell you which ones to do, but I want you to do a couple problems where you have solids that you can't envision what they look like. You're just given the base and the cross-section. And then the other type of problem is the solid of revolution, and I'd like you to do rotating about the x-axis and the y-axis and determining cross-sections to be either circular or annulus shaped.